Mark Rader is Senior Consulting IT Specialist with IBM. He's been in the business for over 30 years. We're here to talk about Db2 12 or ZOS, memory exploitation for performance benefits. So good morning, Mark.
Thank you, Dan. Mark Rader with Washington Systems Center. They keep changing the name of the organization. So even though I live outside Chicago, I'm part of the WSC. And I've been, as Dan said, I've been doing Db2 for ZOS for a long time, back before it was ZOS. If you have questions, please ask. I think I've got enough time to handle most of the questions that come up. Some of this information is based on customer experiences in the early support program, and of course, there's no guarantees that you're going to get the numbers that they got. So what I'd like to talk about is briefly set the stage with the memory and CPU trade-off, and then we'll talk about the three primary features that version 12 is using to do that trade-off, right? Exploiting more memory to get better performance, and those are contiguous buffer pools, index fast traverse blocks, and I'll call them FTBs most of the time. And then there's a new insert algorithm that is available. In the back, I have a list of ways to get performance from exploiting memory that you can do today, version 11, or if you're still running version 10. And then I've got the little warning slide at the end about if you overallocate your memory and you don't actually have that much real, and you try to do some of these things, you could get yourself in trouble. So there's a little, basically a pointer to a couple of Adrian's presentations earlier this week. So what is the memory and CPU trade-off? Fundamentally, if you exploit memory, you spend less on CPU. What we've been doing for many, many years, since MVS was 24-bit, was we've been paying CPU because we were constrained by memory. And now we're able to turn that around and exploit larger amounts of memory to reduce the CPU that we were doing to manage that. One example of a way to use memory to save CPU is by reducing IOs. Not only is there an actual CPU cost to set up the IO before you turn it off to the IO assist processor, but whenever you do an IO and your program takes an interrupt, the odds are someone else is going to come in and start putting their data and instructions in the cache. And by the time your application is able to dispatch again, it's going to have to go out and do, traverse the storage hierarchy to go find your data instructions to get them back in the cache. So if you can avoid an IO and keep running on the processor, you're going to be in better shape. And one of the ways to avoid IOs is to exploit memory, things like larger buffer pools. So memory is cheap, relatively speaking. I'm not a hardware salesperson, but I do know that when you go through a migration from one hardware generation to the next, if you triple or more your memory allocation, the discount is substantial. Before my colleague, Judy Ruby Brown, retired, she figured out that she spent more to get her hair done than someone would have to spend for a gig of real storage. So memory is great, but if you're short on memory, you're going to cause all sorts of problems. So make sure you have the real memory before you take advantage of the things that we're about to talk about. Before I talk about the version 12 features, I'm going to have a one-page reminder about continuous delivery. If you did not see John Lyle's presentation earlier this week, he spent an hour talking about it. The important thing I want to stress is when you first migrate to version 12, you're going to be in function level V12 R1M100, which is basically the equivalent in the old days of version 11 conversion mode. There are some of the features I'm going to talk about will be available at V12 R1M100. Once you've made the decision never to go back to version 11, you can then set function level to V12 R1M500 and something. Right? 500 is what the ESP customers were doing. 501 is available today. 502 will be coming sometime. We haven't announced when. Some of the features we talk about today are going to behave differently or won't be usable until you get to M500 or 500 and something. And if you need more detail on this, again, John Lyle had a session on Tuesday, 21.372, an introduction to continuous delivery. All right, so let's talk about our actual features. The first one I want to talk about is a feature called contiguous buffer pools. We've always liked the idea of keeping our indexes and table space objects in memory, right? We've wanted to do this ever since DB2 was a brand new version 1, release 1 system. That's what the buffer pools are about, right? Keeping your things in memory, that's where DB2 is going to operate on them. The larger we make those buffer pools, the fewer IOs we're going to do. That's the fundamental idea. Starting in version 10, DB2 provided an option called page steal none, where you basically tell DB2, I have sized this buffer pool large enough that all of the objects I've defined there will fit. And therefore, I don't have to do any, I shouldn't have to do any management, I shouldn't have to do any prefetch, and DB2 will treat the buffer pool differently. And in fact, DB2 would stop paying attention to the LRU chain and would do a lazy load. Basically, would prefetch the objects in at first open, fill them in the buffer pool, and then be more effective as you went on during the course of the day. There were still some challenges in version 10 and 11 with page steal none. DB2 would still maintain hash chains and LRU chains behind the scenes, because hash chains is how it found where the pages were, and because if it did, if you were lying, if the objects didn't actually fit, DB2 would eventually have to get rid of what was in there. In version 12, we're going to extend the idea of page steal none. And if you define a buffer pool with page steal none, and when you open an object in that buffer pool, DB2 is going to prefetch that object into the buffer pool, and it's going to lay it down contiguously the way it is on disk. So page 0, page 1, page 2, and so on, right next to each other. And what this is going to do is reduce the amount of get page and release page processing DB2 has to do to go from one page to another. It knows where the row is, it knows what page the row is that it wants, and rather than going out and doing get page, release page to find where that page is, it'll go right to the page. So it's going to reduce the CPU cost for handling this. So no get page, release page. And because we're doing this, we're not going to maintain the hash chains, we're not going to maintain LRU chains. There's going to be less CPU manipulating all of those chains. So the ESP customers saw something between a 1% and an 8% CPU benefit just from doing this. Now, are you going to see numbers like this? I would expect you'd see numbers in this range, but your mileage will vary, right? Depends on how much of this you can afford to do. Again, the concept is you've defined a buffer pool where the objects that belong to that buffer pool will fit, right? So you expect the entire object to be in the buffer pool, and that's what DB2 is going to expect. Now, with version 12, DB2 is going to define an overflow area so that if the objects are not static and they're growing a little bit, DB2 will be able to handle it. And in that overflow area, we're going to do standard, least recently used processing. To support all of this, there are going to be changes to alter buffer pool. So you can say, change it from page steal LRU to page steal none. We're going to be changing to various messages and to statistics. And one of the key changes is that we're going to track get pages in systable space stats and sysindex space stats. And this is for you to go and see how many get pages you're doing for a particular object, and maybe that object is a good candidate to put into a page steal none buffer pool. So at least you can go find the statistics to support your decision. Question? So the question is the overflow area based on the size of the pool? And actually, yes, it's based on VP size. And on the next slide, well, actually, it's the one after this. This is the alter buffer pool changes, but there's a picture on the next slide. So if you alter buffer pool page steal none, that will make the new page steal algorithm a pending state, right? It won't change it right away. You have to reallocate the buffer pool. Because if you're assuming your buffer pool is currently in operation, DB2 is managing LRU chains, and if you want to change it to page steal none, DB2 is going to have to basically rebuild the buffer pool. So it's going to wait until some time that you either change VP size to 0 and then back, which is one way to do it, or the next time you cycle that DB2. So here's an example of issuing the alter and getting the result saying that the page steal none is in a pending state. So here's the picture I was talking about. With page steal none in version 12, DB2 will set aside an overflow area that is going to be a percentage of VP size. That percentage is going to range from 50 buffers at the small end to 6,400 buffers at the large end. And if it's anywhere in between, it'll be 10% of your buffer pool. So if you've got a teeny tiny buffer pool, it'll be 50 buffers. If you have a ginormous buffer pool, it'll be 6,400. So if you're working with large buffer pools, just figure out how large the objects are that you want to be in here, and then add 6,400 and make that the VP size, right? And so that's the range, and then at the very bottom here I give you, right? The sum of the pages of the various objects plus 6,400 VP size, and then you'll be fine. So what's going to happen is DB2 will load all the objects into the green area here and saving the overflow in case some of those objects start growing. So if you anticipate objects in this buffer pool to grow slowly, right, then you give a small fudge factor when you make your VP size. If you expect them to grow a little more quickly, you do need to make the buffer pool large enough because you really don't want to be exercising the overflow area. What you want to do is take messages saying that you're using the overflow area to indicate that it's time to increase the size of the buffer pool. Obviously, we need some changes in display buffer pool. So DSN Baker 402i is changed to include the overflow value. DSN Baker 406 includes the page steal algorithm, and the current and pending. And then if we do end up with overflows, they're going to show up in the DSN Baker 416i message. So I have a couple examples here, right? Here's the new DSN Baker 604i message showing that some pages were read into the overflow area, and then DSN Baker 416i is part of the displayed buffer pool, and you can see that there are overflow sync reads and overflow get pages, because we will still do regular LRU maintenance within the overflow area. We have statistics, changes in statistics to support this. I already mentioned this, right? There's a get pages column with a data type of big int, large integer, for systable space stats and sysindex stats so that you can see what the candidates are for page steal none buffer pools. And we're going to update those every minute. We'll externalize them based on what your stats int is set to in ZParm. And if for some reason you're concerned that you don't have the latest stats when you go to take a look, you can always issue access database mode stats, and that will force the latest updates to be externalized to RTS so you can see them. So if you have small to medium sized objects that fit within a buffer pool, those are obvious candidates, right? But of course, if you've got large amounts of memory and you want to have large buffer pools, then you can put larger objects in there. So when you think about migration, if you're in version 12 and you do an alter buffer pool to page steal none, you can do that right there in V12R1M100. In other words, what we used to think of as conversion mode. So right after you get to version 12, you can issue the command and it'll work, but of course you have to reallocate the buffer pool for it to take effect. If you have a buffer pool defined with page steal none in version 11, and you migrate to 12, right, part of the migration is that you cycle that DB2. So when it comes back up, it'll behave like a contiguous buffer pool. So any questions about contiguous buffer pools before I move on to index fast reverse blocks? All right. So I think those are a neat option, especially for now that we have more memory to think about, as ways to get rid of those IOs, those pesky IOs that would interrupt your application and give other people a chance to use the processor cache and for their data instructions. So let's talk about index fast reverse blocks. For years, it's been possible to put most or all of your indexes into very large buffer pools in hopes of reducing IOs, right? So we've wanted to do that for a long time. And so in-memory techniques was really about trying to either fit the entire index or fit everything except the leaf pages, right? So you get the root and the non-leaf pages for your indexes, so you're not doing IOs for them. And then depending on your overall storage allocation, it would be a question, okay, could you fit the leaf pages too or not? And then we could take advantage by reducing IOs, but also if we had enough of the non-leaf pages and some of the leaf pages in the buffer pool, we could do index look aside, which is helpful during sequential sort of when you're going sequentially through the index, right? Doing an index look aside doesn't count as a get page, right? If the page is right there, we don't have to go through and do a get page, so it's cheaper. However, this doesn't do much for random SQL. Random SQL typically is coming in from the root and traversing its way through the index to find the data that you want. And so whether it's index only or if you have data access, index look aside doesn't help us much. So this is a version 11 or prior type view of random access, right? In this particular case, I've got a 5-level index. So I come into the root, I go through a couple non-leaf pages, and then there's this tiny leaf page down here which points to the data in the table. So if I've got random access going through here, what I'm probably getting is 5 get pages in the index and 1 IO for the leaf page, and 1 get page and 1 IO for the data page. Now I may get lucky, right? I may get lucky and the leaf page is already in the buffer pool, or I may get lucky and the data page is already in the buffer pool. But for sure I'm getting 6 get pages along the way. So in version 12, with the FTBs, we're making change to Index Manager to try and give the kinds of benefits to random access that index look aside gave to the sequential sort of access. And what we're going to do is for unique indexes where the key is 64 bytes or less, and it doesn't matter whether they're padded or not padded, but as long as they're 64 bytes or less, we can put them, Db2 will track your usage of those indexes and determine which ones are candidates to be put into a fast traverse block. A fast traverse block is a section of memory allocated outside of the buffer pool where Db2 is going to lay out the root page and the non-leaf pages so that it can traverse, if you will, the root and non-leaf pages without doing get page and release page. So that's where the CPU savings comes from. The FTB is as outside of the buffer pool, so it's additional memory. So that's, we're trading off memory for performance here. And how Db2 determines that the index is a good candidate is that there's a task out there, right? That's sometimes called a daemon, but the task is a enclave SRB, so it's zip eligible, and it's running under control of Index Manager, and it's going out and monitoring how you're using the indexes. And as it goes through, it's going to keep track. Okay, are you traversing the index in a random fashion? Great. Are you index only? Even better. Are you doing index look aside? Okay, you don't get any points for that. Or are you maintaining the index, right? If you're doing lots of inserts or deletes and moving index entries around and adding non-leaf pages, then you get negative points, right? And as it tracks the points, it's going to say, this index is doing lots of random access, lots of traversals. This would be a good candidate for an FTB. Why don't we allocate an FTB, put the root and non-leaf pages over in this FTB, and save some costs for your processing. If an index gets put into an FTB, it's not permanent, right? Db2 keeps score, and if after a while you stop doing a lot of random stuff and you start doing heavy batch where you're doing lots of inserts or you're updating key columns and moving things around, and you end up having to maintain the index tree structure, well then there's no sense using an FTB because now you're maintaining the tree structure in the buffer pool and the FTB isn't doing much for you. So we'll get rid of the FTB for that index, right? Or we'll just stop using that index will stop using the FTB. So you might see it, use it for a while and then not. And if you have data sharing, how many of you are data sharing? Fair number. You could have an FTB allocated on one member and not on another member, right? Because each one of these is what's going on with a particular member. So this member might be doing lots of random access and getting great benefits out of the FTB. And this member over here might be doing more batch sort of things where we're maintaining the index structure. Now, if there's too much index maintenance going on, it's going to end up affecting the other member, right? But maybe you'll have a score that's high enough over here to maintain the FTB, even though this member doesn't have one. So here's the picture to go with that. I still have a 5-level index. I've still got my row in my data table, but now I've got an FTB allocated up in the upper right. I've got the root page and the non-leaf pages laid out here. And so DB2 will just go and ping through this to find the leaf page and then the data page. So in this particular example, instead of 6 get pages, I end up with 2. There's going to be a lot of significant opportunity for savings here. Now, you have some control over this. This will be on by default, right? The default setting here is auto, in which case DB2 will set off this task, determine which indexes are good candidates, allocate storage in FTBs. Because this is extra memory outside of your buffer pool, if you don't have the extra memory, you might want to turn this off. But assuming you have sufficient memory, then just let it rip, and DB2 will handle it for you. So the default is to take 20% of the allocated buffer pools or 10 meg, whichever is larger. So if you have tiny buffer pools, DB2 won't allocate anything less than 10 meg. If you have ginormous buffer pools, DB2 will take 20%. Or you can turn it off, or you can decide how big you want the FTBs to be. And you can specify anything. Now this is a typo. That 500 is actually 10. I thought I fixed it. So that 500 is just, that's an illusion. That's actually a 10. I'll update it and send the new version to in. If you change the ZParm to disable, DB2 will stop using FTBs further. And then I did change it down here. DBA can specify any number between 10 meg and 200,000 meg or 200 gig. So I already mentioned that it's unique indexes. It does include, if you have index with include columns. How many of you are using include columns? Couple? Okay. So if you have include columns, as long as they're less than 64 bytes for the total length, DB2 will use that, just the whole key. And then this is the scoring I was talking about. Every time you do index traversal, you get a point. If it's index only, you get 2 points. If you're doing index page splits, you lose points. And you lose points on look aside. So as your score changes over time, DB2 will then look at an internal threshold, and we call it an internal threshold because that gives us the right to change it if we want to make it more optimistic or less optimistic. There is additional control beyond the ZParm. There's a table where you can say to DB2, I really want you to use FTBs for these indexes. It won't force it. We're still going to do the count, right? But you can say, I really would like it. Or you can say, for this index, I don't want you to use FTBs, right? Maybe because you know that the random pattern you have is so infrequent that even if you got a good score and it's suddenly allocated, that you're going to turn right around and do all this work, and there's no point having DB2 waste the time on that index because you've got other indexes you'd rather have in the FTB, right? That sort of thing. So how many of you are using the table to manage pseudo-deleted index cleanup? Do you know there's a catalog table where you can manage that? This is a similar concept, right? If you're not using that table, then telling you, we need to have a different discussion about that. So if you indicate in this table that you want to disable it for an index, DB2 won't try to allocate the FTB. But if you indicate, yes, I want it allocated, DB2 may, depending on the score it comes up with. And of course, you want to see what's going on, right? So we're going to change display stats, and you can say display stats in memory usage. My keyboard can't type that many characters in a row without making a mistake, right? It's not my fingers, it's my keyboard. So my keyboard, I think, would be much happier with display stats IMU, right, in memory usage. And you would get something like this. It would tell you the DB ID and the PS ID, and the index name, and that it's out there in the FTB and how much storage is allocated. There's also IFC ID 389, which is part of Stats Class 8, or IFC ID 477, which is a performance trace, which will keep track of which objects are being written out, which ones are taking advantage of FTBs and when. So you can track all of this that's happening in your system. So where is the best opportunity? So I mentioned random access. So the best opportunity is going to be heavy read, right? However, so initially I'm going to say, okay, insert, update, delete, maybe not so good, but if you have a lot of free space and your insert, update, delete processing doesn't cause you to do lots of index maintenance, then you might still get a good score and be able to use the FTB even though you're making changes in the index. If you don't have a lot of free space and you do a lot of insert, then you're going to be maintaining the index tree structure, and that means a lot of work, index page splits, that sort of thing. So random insert and delete may work, again, depending on the percent free. Now, our ESP customers had, they got a 9% reduction even on a 3-level index. So 3-level index means you avoid the get page for the root and 1 non-leaf page. So that's avoiding 2 get pages, and they still got a 9% CPU benefit on their workload, right? And then another example with a 4-level index got up to 20. Pretty sure that's a 5-level index. Again, I have problems with my keyboard. I type 5, it puts up a 4. Now, there's no way I can sit here and guarantee that you're going to get 23% of a 5-level index, right? But that's one data point out of our ESP customers. We have similar numbers from lab measurements, and the lab measurements, again, aren't going to look like what your workloads look like. So this would be a good thing to try out before you rely on the results in production. When you migrate to version 12, fast reverse blocks are available in V12R1M100. So right after you migrate, if you don't turn it off, Db2 will start tracking this and looking for candidates to allocate in FTBs. If you're one of the data sharing shops in here, you can use FTBs unless your index is group of pool dependent. At that point, we'll stop using the FTB. Once you go to V12R1M500 or beyond, then we can use FTBs even with group buffer pool dependent indexes. So you might, depending on how closely you're watching, you might see, if you just accept the defaults and you migrate to version 12, you might see FTB start popping up, which is potentially good, right, as long as you have the storage. And then you might see them disappear all of a sudden if another member starts doing something and making it a group buffer pool dependent. So one thing I should mention that I didn't include on here is I just had the thought, and then of course it disappeared. Migration, version 12, group buffer pool dependent. It'll come back to me, I hope. So any questions on FTBs? Okay, the final thing where I think of version 12 as taking advantage of more storage. Oh, I know what it was. We're not going to allocate FTBs if you're paging, right? Remember how I said early on, we're all talking about trading memory for CPU, but you need enough memory? If you're paging, Db2 is not going to allocate an FTB. One of the ESP customers kept trying and trying and trying. They kept changing their SQL to make it more and more and more random. And finally, they gave up and they said, why are we not getting FTBs? And well, it was the test environment they had didn't have enough real memory and they were paging. And that's one of the things Db2 is going to check, right? It's going to keep track of all the scores, but if you're paging, it's not going to bother because paging is bad for bad for your system. It's definitely bad for DB2. So if you're paging, we're not going to do that. Okay. Yes.
In the table where you can exclude tables, can you specify time slots?
Okay, so the question is, in the sysindex control table where I can encourage or discourage indexes to be FTB candidates, can I specify times? And yes, you can. It's a very similar structure to the one for pseudo-deleted index entry cleanup, where you can specify days of the week or days of the month and time periods where it's encouraged or discouraged. Okay, so let's talk about the new insert algorithm. Insert is one of the interesting challenges, depending on your industry and what you do. Sometimes getting the data in really quickly is a big deal. And there are, there's load opportunities, and insert is another way to get the data in. Sometimes these are really performance critical. And performance for insert processing can vary based on a number of different problems, and the bottlenecks could be quite different depending on your workload. So if you have a lot of indexes, that's bad for insert performance. If depending on your log configuration and whether you're doing synchronous PPRC, which is one of the global mirrors, I don't remember which one, but if you're doing that, sometimes just the log write-o is going to be the thing that's the bottleneck for insert. Another one is data space search. So if I have processes that are trying to insert into the same object, and I have multiple processes coming along, and they're trying to find where the next page should, where that next row should go, what page should it go on, right? There are challenges, serializing that access. And then, of course, if you're doing format writes, I already mentioned PPRC, or if you've got network issues, depending on how far away your disks are and whatnot, there are a number of things that can impact insert performance. And what I'm talking about here is this one that's highlighted, right? Data space search. So if you have an insert process where the bottleneck is data space, is searching for where that row should go, this algorithm will help you. If you have one of the other problems, this algorithm isn't doing anything. So I'm calling it here insert algorithm 2. It's been sometimes called smart insert or fast insert. And again, this may deliver benefits in an unclustered insert scenario, thinking of like a journal table. Unclustered is important here. If you want your inserted rows to be clustered in a certain way, this isn't the answer, right? This is just if you can handle the rows and then deal with them later, potentially reorging them later if you so desire. So the key thing here is if you can tolerate unclustered inserts and you have concurrent insert activity, one thread isn't going to cut it, right? You need multiple threads, maybe tens or hundreds of threads. That's what we're looking at, right? We got lots of insert going on into a table here. And it's not just concurrent, but the problem that you're experiencing is that space search or false leads on where the data goes is what's inhibiting you. So we can use this new algorithm for universal table spaces. You knew that was coming, right? Because all of the new exciting stuff comes with universal table spaces. And they have to be defined with member cluster, right? Doesn't matter whether you're append yes, which puts things at the end, or append no, just member cluster. Now, those of you who are data sharing are probably familiar with member cluster. But you can define member cluster even in non-data sharing, right? It was invented for data sharing, but member cluster really just says to DB2, I don't care whether the things I'm inserting are actually in the clustering sequence, right? If you say member cluster, what you really say is, I want a different way to use the space map pages, and I want to control where the rows go differently, right? Originally for data sharing, but I can specify it in non-data sharing, and I can get this benefit in non-data sharing too. So you define a UTS with member cluster, and then DB2 will take the new insert algorithm to reduce contention on where those concurrent inserts go. I've got a picture of how it works, but first a couple warnings, right? Your mileage may vary. Some insert workloads aren't going to see any benefit, right? Especially if they're constrained by index maintenance, for example, or log write delays. Some insert workloads will see significant improvements. And of course, if space search was your problem and you solve that problem, then you'll discover what the next bottleneck is. And you'll have an opportunity to submit an RFE so that we can fix that one. Load share level change is just an insert under the covers, so it could potentially benefit. And if you do lock escalation or lock table in your SQL statement, then we will not use insert algorithm 2. Now, this one needs to be version 12, V12R1 M500 and something, right? So you need to be at function level 500, 501, 502 when it comes out, which basically says you've gone through the migration, you're never going back to 11, and you said activate function level V12R1 M50 something, and then insert algorithm 2 is available. So here is just a view of what the changes are between 11 and 12 if we take advantage of this new algorithm. So if we look at application response time, we see that we've been able to reduce the response time to the application. The part within DB2 was significantly reduced. There's a little bit of savings in CPU and a significant savings in get page in one particular measurement. Now, another thing the lab did was they took a version 11 PMR that had been opened about an insert problem, and they said, okay, let's recreate that problem in the lab, and let's see what we can do with insert algorithm 2 to solve the problem. And so they looked at this and the other way around, right? They looked at the throughput, how many inserts per second, and for this particular scenario, they went from 2,700 inserts a second to over 65,000 inserts a second. And their total CPU per commit dropped significantly. So that's another way of looking at it, right? Another use case for this one particular customer problem. And then the text down at the bottom gives you the background of what was going on. In this particular case, it was 800 concurrent threads. When you migrate to version 12 and you're comfortable that you won't ever go back to version 11 and you're ready to take advantage of some of the new features of functions, and you activate function level V12R1 M500 and whatever, algorithm 2 is the default, right? ZParms, we give you a new one, default insert algorithm, and the default is number 2, which is insert algorithm 2. So after you go to V12R1 M500 or later, that will be the default. If you're still in M100, think conversion mode, then of course the existing insert algorithm is what you're going to see. You can override the ZParm at the object level, either with a create or an alter, right? If you create a table space, the default is to say what's in ZParm, or you can specify I want the old algorithm, or you can say I want the new algorithm. Or if you already have a table space and you're doing an alter, then you can say alter for basic or alter for algorithm 2, right? 1 or 2. So whichever way you want, you take the ZParm default or you can specify it by the object. So I've been waving my hands around, but I've got a picture here to show you the idea behind this. In version 11 or before, if we have multiple threads that are trying to insert rows, they may learn that page A is the empty page. And each of these threads will learn that page A is the empty page, and then it's a race. How quickly can they get to this page? And of course, then they get to take turns getting the latch on the page to physically put the row on the page, right? So it's very possible by the time thread 3 has waited for its latch so it can insert the row on the page, that thread 1 and 2 filled up the page. And now thread 3 has to go back and look for another page. So that's the challenge. So that's what that red star, which should have shown up there, that was the contention. So in version 12, the idea is DB2 is going to have a pipe full of empty pages. and it's going to pass these empty pages to the threads, and it's going to assign a pipe to each one of the threads. So thread 1 will have a pipe of empty pages that it can just slam rows into, and thread 2 will have a separate pipe, separate pages that it'll slam rows into, and thread 3 would have another pipe with its own pages. The idea is that none of the threads are trying to put a row onto the same page. And because DB2 can allocate pages to the pipe asynchronously ahead of time, right, then we shouldn't be waiting very long as these threads come to do their inserts. They're just going to pop, 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 right? Any questions about this? Okay. So again, concurrent threads, right? UTS, member cluster. All right. I've got a few minutes left. I've got a single slide here. All the interesting things we could do to trade memory for CPU in version 11 or before that still apply in version 12, right? If you haven't taken advantage of them, you can look at them again, right? Making local buffer pools larger, making group buffer pools larger, using page fix for the local buffer pools, using large frames for the local buffer pools, right? Those are all things that were ways to trade memory allocation to save CPU. And those have been available in version 11 or before, and you can still, if you haven't done them yet, you can still do those. If you're not getting thread reuse out of your IMS or CICS transactions, you should look into that. Hopefully you've been getting thread reuse out of batch. I put that in parentheses because thread reuse in batch is almost a no-brainer, right? Because batch is going to run on the same thread, and if you can get away with release deallocate, and it's not going to collide with other things, you can get great thread reuse and great performance that way. Thread reuse and release deallocate for IMS or CICS or DDF, right? Says if I don't have to deallocate the thread, then I don't have to spend the 50,000 instructions or so to reallocate the thread, and I also get to save all the resources that DB2 has accumulated for the life of the thread. Of course, thread reuse and release deallocate, especially release deallocate, comes with this, I'm not going to call it the 80-20 rule, but you want your common transactions or workloads that are almost always going to be executing anyway to be the ones that you do this for, not the ones that occur infrequently because there's extra work setting them up. Another way to invest memory and save CPU is by making your global dynamic statement cache bigger, by taking advantage of, hopefully, of parameter markers and literal concentration. You can even make your local statement cache bigger. How many of you know that you're using the local statement cache for dynamic SQL? Usually we have to talk to DBAs or application types here. So ZParm max keep D says how many statements you can keep on a thread in the local statement cache, right? That default is 5,000. Some customers can increase that, keep more dynamic statements on the local thread. That's going to make the local thread consume more storage above the bar in DBM1, but if you have the storage, this is a good way to get dynamic SQL to start really performing. Dynamic SQL that gets a hit in the global statement cache is going to perform much better than something that doesn't get a hit, right? A short prepare is, depending on your measurements, something like 1/10 of the cost of a full prepare. On the other hand, if I'm running a dynamic statement cache on my thread, and my programmer has written the loop so that I don't do a prepare each time I go through the loop. I do the prepare once, then I execute repeatedly, and I've kept a bunch of those statements on the local thread, I can start getting performance like static SQL, because then I don't even have to check the dynamic statement cache. Another opportunity is max data cache, which defaults to 20 meg. This is the amount of storage per thread that DB2 keeps for handling things like sparse indexing. So it's going to take advantage of thread storage to avoid IOs when it's managing your complex SQL. And then, of course, If you're getting RID pool failures, you can consider making the RID pool larger, and you can consider making the sort pool larger. All ways to trade memory allocation to save CPU. All right. The orange banner says, beware, don't overallocate your memory. How many of you went to one of Adrian's sessions earlier this week? A couple of you? Okay. I would recommend looking them over. We don't want DB2 subject to paging. Now, with my DB2 blinders on, I'm going to say I don't care about the other subsystems, but really, they probably don't want to be subject to paging either, right? But we definitely don't want DB2 to be subject to paging. We don't want the DB2 buffer pools to be subject to paging. And DB2, and probably other subsystems, need to be able to take a dump quickly so you can get a full dump, so that if there is a problem, the lab has what they need to look at it and resolve it and get it fixed. And if you don't have enough storage, if you don't have enough dump space, then you're going to get a partial dump, which means you'll get a partial fix. Actually, you probably won't get any fix. And I'm not going to go into the whole story about the world record for partial dumps, right? 30-some minutes without getting a resolution and causing sympathy sickness across the group. You should be able to take a dump without anybody noticing, right? Except for a systems person who gets alerted that there's now a dump to send off to IBM. And again, I love long-term page fix, love large frames to avoid misses in the translation look-aside buffer. But if you are not careful with those things, you can take storage that either other parts of DB2 or other parts of the ZOS environment need and can cause problems. You have to make sure you have plenty of storage before you do this, and you need to get the calculations right. So there's lots of information about all of these things in the lessons learned from 360 studies, that was Monday afternoon, and from virtually constrained to really overcommitted, which is a whole discussion specifically about going from virtual storage constraint to real storage constraint, right? Because for the most part, we're not virtually storage constrained, right? For the most part, right? Most of our thread storage is now above the bar. Hopefully you've rebound all of your packages since moving to version 10. You've rebound them at least once so that their runtime structures are above the bar, right? And ideally you bind them each new release. So at the very least, you get the new version runtime structure and you re-enable the fast column processing. Even if you keep your old access path, right? The one you're comfortable with, even if it isn't the best one, right? Because you're afraid of that one bad one, please at least rebind your packages in the new release, even if you keep the old access path, right? I say even if because the optimizer teams are doing all this cool work in the optimizer to make your new access paths even spiffier, right? Better performing, so you want to give them an opportunity, but even if you keep the one that you're comfortable with, get that new runtime structure, and that will give you better performance. Okay, the clock is slow. That's what I had, so before I summarize, questions?
Could you talk about M500's introduction of statistics gathering for runstats?
Okay, so the question is about when I'm in version 12 and I've gone to V12 R1 M500 and I'm doing the optimizer input to runstats. Is that?
Turn it on a ZParm that starts collecting for input into runstats.
Okay, so the comment is I turn on a ZParm and I collect statistics for runstats. So I'm going to tell you what I think we're talking about. Completing, yeah, so in version 11, the optimizer would identify situations where it thought it had missing or conflicting statistics. And it would pass that information, it would save that information in the catalog, then it would externalize it, and then you could use it. And the way you could use it is, you could write a bunch of code to go do it, or you could use something like Optimum Query Workload Tuner to go after it, take that, and then make that input into runstats profiles. And in version 12, we're taking that you can do it part, and we're enabling you to put it right into runstats profiles. The assumption is that you've set up runstats to use profiles. So you build your runstats jobs to refer to runstats profiles. The idea then is that the optimizer is going to see where it has missing or conflicting information. It's going to make recommendations and put them in runstats profiles. The next time you're on runstats, pointing to that profile, you'll take advantage of the fact that the optimizer thinks you need to collect whatever this thing is, right? And then the new runstats will gather that whatever that one or two things that the optimizer wanted, which hopefully means the next time the optimizer determines an access path, it'll have whatever it thought was missing or in conflict.
So what's your opinion of it? Is it the best thing since sliced bread?
So the question is, what's my opinion? Is it the best thing since sliced bread? So
Because everything you talked about today is the best thing since sliced bread.
a lot of these things look like the best thing since sliced bread. I would say so my conclusion about the automatic input for runstats profiles, the real limiting fact there is not as many customers use profiles as you might think. And if you have your runstats set up not using profiles, which means it requires you to go through and either take, table all, index all, or go through and specify which ones you want, histograms or whatever it is.
Everybody set up for version 1.2.
Yeah, everybody set it up forever ago and they haven't gone back and revisited. And profiles are, in the grand scheme of things, relatively new. So that's as I see it, that's the only limiting thing is not everybody has gone back and implemented profiles. If you haven't implemented profiles, it's not going to do anything for you, right? And Chuck's comment is, but you should. In other words, you should look at implementing profiles for runstats because it's going to make runstats much better. The vast majority of performance problems that the lab gets relative to SQL and access paths and whatnot are solved by getting the correct runstats. So the latest number Chuck's offering here, the latest number is that 90% of those access path related PMRs come down to collecting correct runstats. Now, that still leaves 10% for other creative issues, right? But if we can solve 90% of the PMRs and remove them, right, that's going to give you more time to focus on other things that are interesting, not to mention Kathy and the level 2 team.
What is the easiest way to set up profiles?
So the question is, what's the easiest way to set up profiles for runstats? I honestly don't know. I haven't gone through it. I'm not a day-to-day DBA, so I haven't gone and done that. Anyone have any input? Anyone here running with profiles? So that's the problem, right? No one in the room is running with profiles. So, but we can find an answer for you.
There was another session a couple of days ago, and they kind of touched on that, and it was a quick do this, do that, but, we'll look at all the details.
All right, so the comment was, one of the sessions earlier this week talked about runstats profiles. It was probably about, was it about the utilities enhancements
I think it was.
on
actually,
Monday?
Yeah.
With my colleague John?
Mm-hmm.
Yes, so he's gone through and done work in that area, and it shouldn't be that difficult, right? If it were that difficult, we wouldn't give it to you.
I was at that session. I believe it is just adding the profile parameter to the runstats.
So Chuck was there, and it looks like it's relatively straightforward. You can add the profile keyword to your runstat statement, and that should, so there is some, you do have to do, there are some things you have to, there's a little oversight needed, but yeah. Anything else? All right, well, let me summarize then. As far as version 12 specifically goes, contiguous buffer pools come in V12 R1M100. They don't occur automatically, but if your buffer pool is defined page still none, it'll happen. And you may want to deploy more memory so that you can either support the existing page still none buffers you have or define your buffer pools with page still none that are currently defined LRU. Another option is You can identify specific indexes or tables and say, you know, I'm going to take them out of their existing buffer pool and put them into this new page still none buffer pool because I know these specific ones are sensitive and I haven't had a reason to isolate them before, but I can now fit them, you know, they're real popular and I can put them here and avoid I/O for them, right? But of course you want to make sure you have the memory to back that. And then for the index fast reverse blocks, those are on by default. They're on in V12R1 M100, and again, that's going to require more memory. When we talk overall about version 12 memory, just going to version 12, DB2 will want in the order of 20% more, not including the buffer pools, right? The rest of DB2 is going to want 20 or so percent more than what it does today. Index fast reverse blocks are on top of that, right? So you got to plan for more memory usage there. And then insert algorithm 2 isn't available until V12R1 M500 or 501, which is currently available, or 502, which will come sometime. But insert algorithm 2 is on by default. And this will require some additional memory. When I say some, it's because we need memory for those pipes of pages, right? When DB2 starts setting up a pipe with new pages in it, that's all being carved out of real memory, right? So we're going to need some. How much? Well, it depends, right? How many things are you using the new insert algorithm for? How often are you getting this concurrent access? And how often is DB2, you know, building and filling those pipes? So that would be a little harder to calculate, but that's going to be some. And in each of these cases, by allocating that memory, we should be able to save performance. So thank you very much for showing up Friday morning. Really appreciate seeing this many people here, reasonably awake. I guess being first thing in the morning, that helps. Coffee's still running in the veins. If you think of any questions after this, send me an email and I'll do my best to get you an answer. So thank you very much.